Right, modulus function, equations and inequalities this time. So we're looking at how we use the modulus function to solve equations and to solve inequalities. So starting with equations first, if you've got the equation, the absolute value of x plus 2 equals minus 1, how do you know about solutions? You should be able to see that it has no solution, but can you figure out why? If we were to draw this, are we ever going to end up with a negative value? Well, no, because the whole of our expression has been enclosed in these modulus signs, which means it's always going to be a positive value, so there will never be a solution for this one. How about if we try a different one though? How about if we've got, let's go with 2x plus 1, absolute value of that is equal to 3. So we could sketch a graph to give us an idea of what's going on. That would probably be a really good place to start. So we know that our graph has gradient 2, goes through the y-axis at 1. So it's going to look something like that. But down here, instead of going off down this way, it's going to reflect like this. We're trying to find a solution for where it's equal to 3. So you should be able to see there are going to be two places where we have an intersection. So there are going to be two solutions for that. And our two solutions are when x is 1 and when x is, when our solution is 3, but also when our solution was minus 3 and has been changed by this. So all you would have to do is just solve the equation twice, once for the positive value and once for the negative value. Okay, nice and simple. So to solve this one, then you'd obviously take that over there, and you'd get a solution of x is equal to 1. And if you do this, that would give you a solution of x equals minus 2. So they're your two solutions, x is 1 and x is minus 2, because our two y values are both 3 at the moment, but they would have been 3 and minus 3. So they're the bits you need to solve. So sketch, really helpful when you're solving these. It's the same as when you do inequalities normally. When we were solving quadratic inequalities, for example, it really helped to sketch them so you could see which bit was in the range that you were trying to solve and which bit wasn't. Same with these ones, sketching it will really help you. So always worth doing at least a quick sketch. Let's have a look at a slightly more complicated one now. We've got f of x is equal to x plus 1 and x minus 5 multiplied together. So we're solving the absolute value of f of x is equal to 8. So if we do our sketch, it's going to look a little bit like this. We've got a graph that looks like this and like this. So that means that's going to bounce back up here like that. And we're solving it for the value of 8, which is going to be somewhere around here. It's not a very accurate sketch, so while it might look like it's on the axis, it's probably not. So we'll solve it properly. Okay. It might help to say that that's a value of 2, 9. It can help to say that that's minus 1 and that's 5. The more accurate you can be with your sketch, the better, probably. So for this to equal 8, either we've got f of x is 8 or negative, or f of x is negative 8. So if we write it out, we can work out our two solutions. So x plus 1, x minus 5 is equal to 8, and we can solve that. And we've also got x plus 1, x minus 5 is equal to minus 8. So we can solve that. So let's take it over here first. X squared minus 4x minus 5 equals 8. So if we take the 8 over, then we get x squared minus 4x minus 13 equals 0. So probably easiest to do this with completing the square. We've got x minus 2 all squared, and then the value that we need to adjust is going to be minus 17 to get us down to this value here. So x minus 2 all squared is equal to 17. If you're not sure about this one, then work through the algebra on your own. X minus 2 is equal to plus or minus root 17. don't forget the plus or minus. Whenever you square root something, you should always have plus or minus. Same as we're doing when we solve the modulus function. You always have the positive and the negative solution, because that allows for the fact that you've reflected. When you square root, you must always have plus and minus. Always, always. Otherwise, Miss will shout at you. So we've got 2 plus or minus root 17. That there are solutions for this one. We're also going to do the same for this over here. And we're going to get x squared minus 4x minus 5 equals minus 8. And if we take that over, we get x squared minus 4x plus 3 is equal to 0. That one's a bit easier. We can factorise it. X minus 1 and x minus 3 is equal to 0. So we get our solutions with x is 1 or 3. So we've got, between those, all of our 4 solutions, the different places that it intersects that line where y equals 8. Okay. So, a couple of harder ones. Let's have a look at what happens when we've got a slightly more complicated function. Right. So we're going to sketch the graph of y equals f of x, and f is the function that's defined by f of x is equal to 3 minus 2 lots of the absolute value of x plus 1. And we're going to state its range as well. So one of the ways we could do that is we're going to look at our graph in stages. So we're going to start with the graph of y equals the absolute value of x plus 1. This is our first bit here. And then we're going to do some different transformations to it, because we know we can sketch that one, it's nothing too complicated. So we've got y equals x plus 1, gradient of 1 goes through at 1. And it's worth noting that it goes through here at 1 and here at minus 1. Okay, so that's our first step. If we then move on to y equals 2 lots of this, then we know that what we're actually doing is stretching it by a scale factor 2 in the y direction, because we could have written this as a half y equals x plus 1 by dividing through, and we know that from our core 2 transformations, the scale factor, if you've got a scale factor of 1 over k y, then that's a stretch in the y direction, scale factor k. So we're going to do a stretch in the y direction, scale factor 2 here, which means it's still going through at minus 1, or touching at minus 1, but now it's going through at 2. So we've just made it a little bit steeper. Okay. The next thing we're going to do is make that minus 2. So we're going to look at y is minus 2 lots of the absolute value of x plus 1. So all we're doing is taking our graph and flipping it upside down. So it's still at minus 1 here, but now it's doing this and it's going through at minus 2. So we're just taking it step by step, and then all we're going to do for the last bit is we're going to say if y is 3 minus 2 lots of the absolute value of x plus 1, then we've translated it up by a factor of 3. So we're going to go from here, still at minus 1, that's still our point here, but it's going to go up 3 here. So it's going to go a little bit like this. Okay, and you can work out a couple of points of where it goes through. If you know that it went through at minus 2 there, it's going to go through at 1 here because it's gone up by 3. That's what we've done, we translated it up by 3. So you should be able to work it through and work out the 2 points of intersection, and you can then quite easily, even without the points of intersection, you can state the range, because the range, remember, is the set of possible output values. There is nothing that is above y is equal to 3. So our range is f of x has got to be less than or equal to 3. Okay, f of x less than or equal to 3. So a couple of different bits that you need to remember. Key points is when you are dealing with a modulus and you're trying to solve an equation or an inequality, then you need to remember to solve for both the positive and the negative. If you're then trying to solve an inequality, it's usually fairly obvious. If you were, for example, trying to solve the inequality of y equals 3 minus 2 lots of x plus 1 absolute modulus, however you want to describe it, and we wanted to solve it for y is greater than 1, then we would know it would be these parts of the equation, and we just need to work out this point of intersection and this point of intersection, and we could say it's between the two things. Okay, so we could solve our inequality by sketching and seeing which portion of the graph is where we need to be. So greater than 1 in this case would be all of that stuff. So you would then write x has to be less than or equal to 1, or sorry, less than 1, but less than 0, and greater than whatever this point is here, and we can solve that using the usual make them equal and see what happens.